Okay, hello everyone. I want to start by thanking the organizers for having us. It's a real honor and privilege to be speaking at Code Blue for the first time. And it's also a real privilege that the lights are on today, because today we're going to be speaking about a piece of malware that's capable of causing a blackout. In fact, it already caused one in Ukraine last December. So I think that's pretty significant in and of itself, but there's more. So this malware, Industroyer, it's the first ever malware designed to attack power grids automatically. And for that reason, we consider it to be the biggest threat to industrial control systems since Stuxnet. My name is Robert Lipovsky, and together with Anton Cherepanov, we analyze malware on a daily basis. In fact, we've been doing that for the past 10 years. And when we discovered Industroyer, frankly, we were blown away. We're based in Slovakia, in Europe. We work as malware researchers for ESET, the cybersecurity company who pioneered anti-malware heuristics and has been innovating anti-malware solutions for the past 30 years. This is the central room of our virus lab, which we call Houston. I think you can guess why. Okay, so let's take a look at our agenda today. First, we'll put Industroyer into context of the other malware that targeted ICS, industrial control systems, in the past. Then we'll explain how it works, and we'll follow up, we'll end the presentation with some final thoughts on the impact that it poses. But first, let's begin by taking a closer look at how ICS targeting malware works in general. So we have an industrial site, which can be anything from a uranium enrichment plant to an automobile factory, and it's got its specialized industrial hardware. And these devices, this specialized hardware, it's controlled by human operators, monitored and controlled by them, and configured from workstations, these ones, typically running Windows. And that was the point of infiltration for all the known ICS targeting malware families. Now, where these families differ is in their capability and their methods of controlling and disrupting the industrial process. Industroyer specifically, well, as I said, was designed to attack electricity distribution substations. So in the malware, there's a timer. In the analyzed samples set to the time of the blackout in Kiev in Ukraine, and this timer triggered Industroyer's unique payload, controlling circuit breakers automatically through industrial communication protocols in order to cut the power. So now you know what the malware was designed to do. We can go for a break. Just joking. Let's take a closer look at how it works and put the malware into context of the other malware families. So Industroyer joined this elite club of only 3 previously known malware families used in attacks against ICS. Stuxnet needs no introduction, obviously. It was able to reprogram PLCs, programmable logic controllers, to change the rotation speed of centrifuges. Havocs, also known as Dragonfly or Energetic Bear, infected many industrial sites in the past, and it's interesting because it also abused the OPC-DA protocol, which is also abused by Industroyer, but unlike Industroyer, Havocs was only using it for espionage. It didn't directly control the industrial process at the targets. Now, BlackEnergy is a little bit different from the other 3 families. We've been tracking BlackEnergy since 2011, and over those years, there were many campaigns, mostly spear phishing, and we even discovered one time when they were using a PowerPoint 0-day. That was the infamous CVE 2014-4114. And then maybe you heard about this case known as SandWorm as well. So I said there were many targets over the years, and there were many high-value targets. So they included government, media, transportation, and so on. But what's relevant to our topic today are the campaigns against the Ukrainian power grid. So they started in March 2015. The first spear phishing emails that we detected were coming from March 2015. And the attacks culminated on December 23rd in the first ever known malware-induced blackout that affected several regions in the whole country, leaving around 230,000 people without lights for several hours. As I said, BlackEnergy is a little bit different from the other three ICS targeting malware families. It wasn't designed to target ICS specifically, but rather it's a more general purpose cyber weapon. And through its network traversal and espionage modules, some of which you can see in this screenshot over here, it paved the way for the attackers. It gave them access to the target network, and then the attackers used radmin. So legitimately installed remote access software, which was used by the substation operators for remote access, and they accessed this and they were able to manually pull the plug. The good thing about radmin is that it produces logs. So this is the actual log from that afternoon showing the unauthorized accesses from computers which have previously never connected to that network. And this is a video taken by one of the operators sitting behind that workstation while the attackers were remotely accessing their system. You can see the confused voices in the background. The actual SCADA software used.
Богородчанського РЕСу. Диспетчер ніяких дій не робить. Ми також ніяких дій.
And the point of the video is basically, okay, somebody is accessing my system and it's not me who's touching the mouse or the keyboard. So now let's go on to the main topic. So on December 17th, 2016, which was almost exactly 1 year after the previous blackout, we were struck with a sense of déjà vu. There was another blackout, and we started analyzing samples of malware, which became the main suspect, Industroyer. We sent our analysis to Ukraine shortly after, and then we had to wait in order not to interfere with ongoing investigations. We received the green light to publish in June when our public report went out. So a few slides before, I already mentioned what Industroyer can do, what it did, but now let's take a closer look under the hood. So it starts with a main backdoor, which takes care of CNC, command and control communication, and launches all the other components. Now, the backdoor in and of itself isn't super interesting. It's the typical kind of malware, the kind that we analyze thousands of every day. Here is the list of commands that it supports, so I'll just highlight some of the more noteworthy ones. Now, while Industroyer doesn't focus on espionage, like BlackEnergy did, for example, it does provide the attackers some capability of downloading and executing additional modules, as well as to exfiltrate files off of the infected machine, such as this copy and upload file command, as you can see here. And the output produced by this command also gave us a glimpse into the command execution chain and lateral movement throughout the attack. Now, all those commands, all that execution flow was done in multiple stages, as you can see over here. And the main purpose of that was to enable the attackers to stay under the radar. Now, the scripts here, they're not overly interesting, but the MS SQL database and how it was abused is. So let me explain. So during the reconnaissance phase of the attack, the attackers got hold of an in-house custom application used by the substation operators. So here are some screenshots from the documentation of that application. It's a custom app that stores environment layout, ICS process logs, telemetry, stuff like that. It's not used to directly control the operations, so it's more just a logging and environment layout storage application. Nevertheless, they reverse engineered it, and they discovered that the data for this application is stored in an MS SQL database on a server, and the credentials, unfortunately, were hard-coded within the application. So that was a good opportunity for the attackers, and they abused this database to execute a number of shell commands during the reconnaissance phase of the attack. So here are a few other examples of that application. So in order to be able to execute commands from the context of the database, they first had to enable the XBCMD shell capability in the database. And then they were able to launch arbitrary commands. Not only that, but they were also using the database to store binaries, again, something to add stealth to their attack. Also, the last command in this list is quite interesting. It's used for persistence to ensure that the malware survives a reboot. And it does so, it installs itself by pointing the image path registry value of a chosen existing Windows service to a more obfuscated version of itself. There's also a secondary backdoor. It's used as a backup mechanism. Obviously, once the attackers manage to do the hard job of getting inside the network, they want to make sure they stay in there undetected for as long as possible. So they implemented this additional backup backdoor in case something happens to the primary one, in case it gets detected or disabled. Now, the interesting part about this secondary backdoor is that it masquerades as a Trojanized and otherwise fully functional version of Windows Notepad, which it replaces in the system since it already got hold of admin credentials. Now, also a similar technique to this was used by the Dragonfly, the Havoc's malware in campaigns this year. So there are a couple of additional tools. The noteworthy ones are a custom port scanner, for example, which the attackers chose to use instead of Nmap, something which they could have used that's readily available. There's also the denial of service tool, but I'll talk about that later. So here's an example of how the port scanner executes, and an example of some of the ports that it's scanning on the target network. You can see that some of the ports are related to industrial control systems. So this was the lateral movement phase of the attack. But now we're getting to the actual interesting part. We're getting to the actual execution of the attack, to the payloads. So during our analysis of Industroyer, we identified 3 distinct ways in which it attacks, which it affects the operations at an electricity distribution substation. Now, firstly, and most importantly, it can directly control the industrial hardware on site. So you might be asking, for anyone who's not an industrial control system expert, so what is this hardware I keep on talking about? So they're basically protection relays, such as these that you can see on these screenshots from 2 different vendors which are common in Ukraine, Siemens and ABB. And there are many different types of these protection relays, but basically their function is to control to open and close circuit breakers for various purposes without going into an electrical engineering 101, purposes of protection, balancing the power grid, and so on. Now, this hardware, it's configured and monitored, as I explained before, by specialized SCADA software running on regular workstations, typically running Windows. Some examples over here. And remember this SCADA software because it'll be interesting towards the end of our presentation. So those are the applications, and the communication between the controlling workstations and the protection relays takes place over one of several possible specialized industrial control protocols. Now, there are several of such protocols used throughout the world. Some of them are regionally specific. Some of them operate over a serial connection, others over TCP/IP, but the overall idea is the same. Now, it's important to note that Industroyer abuses these protocols. There are no actual exploits involved, no software vulnerabilities. It uses the protocols in the way they were designed to be used, but they were designed decades ago without security in mind. And with that, I pass the microphone over to Anton, the lead in our industrial analysis, to walk you through the payload.
Hello. Robert already said about exact timing of Industroyer attack, and that's a job of launcher component. The launcher samples we analyzed would launch the individual payload on December 17, shortly before power outage. We identified models capable of controlling devices through 4 different communication protocols: ISC 101, ISC 104, 61850, and OPCDA. Most of them are DLL files with their own configuration. So first one is OneOne. It requires a configuration file. Here is an example. It's not a real example that was used, but it's a reconstructed one. So it communicates over serial connection, and the core ports to use are defined in the configuration by attackers. And first thing it does, it kills legitimate process on the workstation responsible for controlling the devices and takes over. So attacker can define name of this process in configuration. These devices, they operate on something that called IOA, Information Object Address. Think about them as network ports or registers. There are several different types, IOA types, but payload is interested only in those 2, which can accept commands. It goes over defined range of these IOAs. Here in the configuration, we have 2 IOAs ranges from 10 to 15 and from 20 to 25. So it goes over these ranges defined in configuration and sends the command sequence: off, then on, then off again. The idea behind 104 payload is very similar to 101. It sends on or off command to devices, but there are few differences. It works over TCP/IP instead of serial. It has many more configuration options, and it's possible to define multiple station entries. So it will connect to, when these entries are defined, it will connect to devices in parallel. And main option is operation mode. There are 3 different modes: range, shift, and sequence. Both for 101 and 104, attackers, they don't know the types of IOAs. So they have to do some kind of brute force to find out which will accept these commands. So first two modes, range and shift, they used to discover right iOS, and sequence is used once they are known. The payload constructs packet on the fly, and thankfully to Wireshark we can dissect them. As you see on this example, it sends a single command on IOA number 10. And here we have on command. Payload can also write to the console, and here is an example. So attackers, they can see real time what's going on. It supports not only logging, but also, not only console output, but also logging. This example demonstrates capability of payload. It tries to switch circuit breakers to on or off in infinite loop. But exact logic, it depends on configuration. So it can send either on or off continuously, or flipping back and forth between iterations. So in this example, at first it sends on command, then it switches to off command, and in next loop, here is the loop, and in next loop it sends off command. So next payload is 61850. It's a bit different, and bit more advanced. Like 104, it operates over TCP/IP, but it can function even if IP addresses not specified in configuration. It has auto discovery feature, so it scans port for all IP ranges in this network, and then it can connect to these devices. It does not operate on iOS, but on named elements. It looks for these hard-coded names. They correspond to circuit breakers, this CSV. So it's a different approach, but same purpose, to open or close circuit breakers. And the last payload is a step above the rest. It's not more advanced, but it operates on higher software abstraction level. Technically, OPCDA, it can be built on top of 101, 104, 61850, or even Modbus. It uses distributed COM to discover all OPC servers running in the network. It obtains named items, and it searches for these specific tags. Then it writes byte value 1 to items with these tags. But what does it mean? This tool from ABB, it helped us to translate the command into better human-readable form. As you can see, this tag, ctl open off, is breaker open execute command. So again, the purpose is the same, opening circuit breakers. And analyzing these payloads, it's an easy task for a skilled reverse engineer, because they are not obfuscated in any way. The only thing that can and will slow down your research is this annoying COM stuff. So to help analyze any future malware that would use this OPCDA, we released this IDA Python script. So that's how the code of Industroyer looks like when we open it in IDA. And that's how it looks when we applied this script.
Thank you, Anton. Now, I think all the reverse engineers in the room can agree that that looks much better, right? So all of these 4 payloads that we talked about serve a similar purpose, to open and close circuit breakers. So the effect, we know what was the effect. We know that there was a blackout. So de-energizing a substation is the obvious outcome of these operations. But there are other theoretical possibilities what the attackers could have tried to accomplish. As I talked about BlackEnergy, we know that it's possible to cause a blackout using much less sophisticated malware than this. And in 2007, you might remember the Aurora generator test. There's a really nice video on YouTube. If you didn't see it, I recommend you watching it. It demonstrates how out-of-sync closing of protective relays, exactly what Industroyer was doing, can lead to actual physical hardware destruction. So it's a video how a diesel generator blew up by issuing out-of-sync closing of protection relays. Now, we don't know if the attackers actually wanted to do this kind of damage or whether the substation was susceptible for this type of attack, but it's a theoretical possibility. So the second type of functionality, so that was the first one, directly sending commands to the hardware, opening the switches, opening the circuit breakers. And the second one, which we identified in the Industroyer framework, is rendering protection relays irresponsive. So that's done through the denial of service tool, which I mentioned in the overview scheme. That denial of service module does that by exploiting the vulnerability in Siemens cProtect devices as described in this ICS cert advisory. More specifically, it does so by sending specifically crafted UDP packets to port 50,000, exactly what this code in this snippet is doing. Now, knocking these devices out serves to amplify the impact of the payloads that Anton was previously talking about. Now, it's important to say that Siemens did patch this vulnerability in a firmware update quite some time ago, but you can probably guess how often these devices actually do get updated. The third and final type of payload functionality that we identified in the Industroyer samples we analyzed is the data wiper module. Its purpose is to make recovery from the attack harder. It goes not after the protection relays, their so-called intelligent electronic devices, but after the workstations used to configure them. It's executed by the launcher module, either 1 or 2 hours, depending on the sample. So 1 or 2 hours after the ICS payloads were launched. So if you remember the configuration software I showed you earlier, well, this module wipes files belonging exactly to those kinds of SCADA software, some of which you can see on the slide in the list over here. Now, furthermore, it renders the machine unbootable by corrupting the registry. And finally, it crashes the computer by killing all, including system processes. So what's the overall effect? As a substation operator, you have your circuit breakers continuously being reopened. Your protection relays are not responding because of the denial of service attack. And when you go and sit down, try to fix the problem, you find that your SCADA software is gone. So it's a pretty nightmare scenario. And it's another demonstration of the importance of backups. And it's really, really incredible that the Ukrainians last December were able to recover from this attack in such a short time frame because the blackout last December only lasted for about 1 hour. In comparison to the blackout in 2015 caused by BlackEnergy, which had the duration of several hours. Now, as we've shown you, some of the modules within the Industroyer framework are vendor agnostic. They're basically the modules speak the protocol of those devices, and they're implemented across various different device vendors, such as IEC101, IEC104, for example. While others are specific to a certain brand, a specific vendor. So some of them were targeting Siemens, the denial of service module. The OPCDA that Anton was talking about is going after ABB devices specifically. And we also discovered this General Electric firmware, this boot code, in the folder where all the other malicious files were stored. Now, we don't know whether or how it was used, but it just shows, it demonstrates the capability of the attackers to adapt to whatever vendor their target might be using, and thus making it, increasing their capabilities. So it's not just limited to Ukraine, it's not just limited to a certain vendor, but they can go after whoever they choose. So that brings us to a couple of takeaways from this presentation. As we've shown you, as we've seen, Industroyer's capabilities are rather versatile. It was the malware that caused the blackout, the last blackout in Ukraine, but it's also configurable. It can be repurposed to attack power grids around the world. So it's not just something that can only happen in Ukraine. It's a scalable and dangerous weapon against industrial control systems, as we've said, the biggest since Stuxnet. But the gist of the threat is not just in the malware itself, it's in the skill and the dedication of the malware operators. So it's not just about being able to code the malware, but it's about their ability, which they demonstrated in Ukraine, of becoming familiar with the architecture of the industrial site they want to target. Because remember, this is not the common typical task of regular cyber criminals or even APT threat actors, who are conducting espionage, but operations like this require a lot of homework, which this group did. So they had to first find out what devices there are, what commands to send to these devices, and what will happen as a result.